Hello everyone, in this video we will talk about more details of virtual memory. We will introduce how to implement the page table, how to organize the page table. So this is actually the detailed information about how to implement virtual memory technique. And we will go through a couple of examples and you will have similar problem as the slides example in your final exam. Sorry. So I have to say 5-star because you will have example similar problems as the examples in this slide in your final exam. So of course I will post a review list next week. I will post the review list. So in the review list for your final exam, then you will see all the required topic, and you will know which part is required. So have to emphasize in the video. So pay attention to the examples included in the slides. So last time we have talked about the virtual memory technique. So for any program, we always assume there are 32-bit memory address. So that actually means we always assume we're using a 4 GB memory, which is not true. Of course, your physical memory can be any size. So, and then we introduced the technique called virtual memory. Actually, we just add a translation table between the physical address and the virtual address. So for the program, we always have a virtual address 32 bits long, and for the real physical address, it could be with any length. It could be with any length. So by checking the table, by checking the translation table, then we could actually determine where this piece of data should go. So how to implement this, and another concept should be included, and you will have this introduced in a lot of other classes and a lot of other applications, and you will learn this again in your operating system. I'm pretty sure you will have related concepts introduced in your high-level classes. So page table. So the translation table we have introduced, the mapping we have introduced the last time is called page table. So what is page table? So it's actually a map. It's actually a map which maps the every virtual memory to every physical memory, every virtual memory to every physical memory. And inside of the mapping, of course, each mapping pair, such as the virtual memory, blah, blah, maps to the physical memory, blah, blah. So this mapping pair is called a page table entry. It's called a page table entry. For each mapping, it is one page table entry. So you may have many, many page table entries. So the problem here is, suppose we want to do a mapping for each word address. A mapping for each word address, and how many words we have for the 32-bit virtual address. So we do have 32 different locations in the virtual memory, and that's by byte, right? So we, of course, will have 2 to 30s. So 2 to 32 bytes in my virtual memory. Actually equals 2 to 30s. 2 to 30s words, right? So in the virtual memory, we have 2 to 30s different location. That actually means I have a billion different locations, different address. And if we would like to have a mapping for each word, then that will actually cause a billion different mappings. And then thinking about the size of this table will be huge. If you have a billion, this kind of mapping link. So, for each of them, you need to have the virtual address plus the physical address. You need to have a really, really huge table. You will have a really huge table, right? So, but the table itself, will cost you 1 GB memory. So, which is impossible for us to keep it, because we do not have that big memory, right? Where we put the table is a quite a really important question. So how to solve this? And how about if we do not do the mapping word by word? If we do not do the mapping word by word, we could actually do the mapping chunk by chunk. So you could chunk, divide the memory, the virtual memory, into many different chunks, And the chunk here is actually called a page. So the original translation table now become a page table, because we can do the mapping page by page, chunk by chunk. We do not have to do the mapping one by one, one address to another address, one address to another address. We could actually map a big group of address into another group of address, such as we can map the address, virtual address, from 0 to 4K and to another piece of address. And the left hand side is the virtual address, the right hand side is the physical address, but you can map them piece by piece. And those two pieces has to be the same size, However, you can dramatically save your mapping. So the map, the page table will become much smaller. So typically we will use 4K bytes. 4K bytes is a popular size. That actually means 1,024 words included in each page. 1,024 words included in each page. So I assume everybody know why 4K bytes equals 1K words, right? So 1K words equals 4K bytes, because one word is 4 bytes. So 1,000 mapping, 1K mapping, 1K actually different address, 1K different addresses are actually included for each page. So this is a popular page size. It doesn't actually mean all the page size should be designed like this. You could have a bigger or smaller page, but 4K bytes is a popular page size. So the table become a page table, and then each mapping again is still called a page table entry. But we will have much fewer page table entries because we do less mapping than before. We will do less mapping than before. So then how about, for example, the virtual address from 0 to 4K is mapped to 4K to 8K. So the first chunk in the virtual address is mapped to the second chunk in the physical address. And we could have fewer chunks in the fewer pages in the physical address than the virtual address. So that's for sure, you could have different sizes. And then your physical address, your physical memory can be much smaller compared with the virtual address you have. But as long as you are able to manage the mapping, right? So even I only have 3 different locations, I do not need to hold all of them together. So some of them can be stored in the hard disk. So, but each page has to be the same size. Right? And how we implement this, this is called address translation. How we implement the page table. This is called address translation. So for some detail, what is address translation? How can we implement the page table? For example, suppose the virtual address is 32 bits long as the Euro address we're using all the time for MIPS. So 22 bits long physical address. That actually means we have 256 megabyte in the real RAM we have installed. So why? 256 megabyte? This is the size of the real RAM, the physical size of the RAM. So this is how much memory you actually have, but we are always assuming we have 32 bits, which is 4 gigabyte, much bigger than this. But your real memory size is 256 megabyte. So 256 megabyte actually means you have 28 bits real physical address. So the size of your physical address is 28 bits long. So why it is 28 bits? Because megabyte here means, so the 256 is 2 to 8 power times megabyte is 2 to 20. Remember a 1K byte, so the kilo here means 2 to the 10th power, And the megabyte means 2 to the 20th power, 2 to the 20th power. And the gigabyte means 2 to the 30th power, 2 to the 30th power. So the megabyte, 256 megabytes means 2 to 28, 2 to 28 bytes, 2 to 28 bytes. 2 to 28 bytes. So the address of the physical address, the length of the physical address is 28 bits long, 28 bits long. And the real address, the virtual address is 32 bits long, 32 bits long. So how can we map the 32 bits to a 28 bits? How can we map the 32 bits to a 28 bits? So that's the question of the detailed implementation for the page table. So the page table need to handle a mapping between the 32 bits data to the 28 bits data. And remember that actually we do not map each word location. We do not map each byte location. We do not map each word location because we implement this table as a page table. So we only map page by page. And how big is one page? Suppose we would like to design a 4K byte, a 4K byte page, a 4K byte page. So a general size page. So the 4K byte here means each page has 2 to each page has 2 to 12 different location because 1K is 2 to 10th power. So 4K will be 2 to 12th power, 2 to 12th power. So if we have 2 to 12 different locations inside of each page, that actually means the lower 12 bits cannot be mapped, and you do not need to do the mapping. You do not need to translate the lower 12 bits. So why we do not need to translate the lower 12 bits here? So I would like to make an example. So for example, suppose you have 1,000 different locations in the virtual address. So 1,000 different locations in the virtual address. And we would like to map each 100. We would like to map each 100 as each 100 different location as a page, right? Each 100 different location as a page. And suppose the physical address has only 3 pages, So the size for the physical address is 300. So all we need to do is, we map the 0 to 100, 100 to 200, 200 to 300, 900 to 1,000. So we are kind of like, so the only thing we need to do is mapping the number from 0, 1, 2, dot, 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 all the way to 10, or from 1 to 10, or from 0 to 9. So we are actually doing the mapping between this number, the 1,000 number, to 0, 1, 2, 0, 1, 2, 3 different index, because you only have 300. So what we are doing is we are mapping the digit in the 1,000 location to this digit, because we have 300 different locations inside of the real RAM. And in the virtual RAM, we assume we have 10 different handles. However, as long as we could map the 10 different page location to the 3 different page location, we are not actually mapping any number, the number. So if you have an address such as 159, for example, and this is the virtual address. Suppose we would like to map it to a physical address, and the physical address we eventually end up with, suppose that's 259. So what we need to do is actually mapping the number 1 to the number 2 here, and there's no translation needed. There's no translation needed between the 59 to this 59, because the first location in this location will map to the first location in the mapped page. the second location in the virtual page will map to the second location in the physical page. The third location in the virtual page will map to the third location in the virtual page, in the physical page. So we do not actually need to map the location, the index inside of the page. We do not actually need to map the location inside of the index inside of the page. We only need to map the page number. We only need to map the page number. We only need to map the page number. So the page offset does not need to be translated. The page offset does not need to be translated, right? So this is so that's why suppose the page size is 4 KB, So we do not actually need to map the lower 12 bits inside of your address, both the virtual address and the physical address. So inside of the physical address and the virtual address, we could leave the lower 12 bits alone, and then we will be able to do the mapping. For example, suppose we want to find out the fourth location. So suppose the lower 12 bits equals 4. Suppose the lower 12 bits equals 4. And then we are trying to map the address number 4 to the physical address. And all we need to do is figure out the higher 20 bits inside of the virtual address, the mapping of the higher 20 bits. And then suppose the first page in the virtual address maps to the second page of the physical address. And all we need to do is find the starting point of the second page inside of the physical address and count to 4, right? Because we are trying to find the fourth location of that page, So we do not need to map the page offset. We only need to map the page index, So then another question, for example, how about if you want to map a 32-bit virtual address to a 8 gigabyte virtual physical address? So as I told you, a lot of your modern computer, they're not using a 4 gigabyte. It's too small, right? So you may have a bigger RAM installed, and your program still assume you only have 4 gigabyte. So of course that's good, So that actually means we have more locations, more pages in the physical RAM than the virtual RAM. So we have more pages in the physical address than the virtual address. And then what will happen? Suppose you still want to do a 4 KB page. So again, 12 bits are used as the page index, as the page offset. So then we will have 20 bits left inside of the virtual address. And we only need to perform the mapping for the 20 bits inside of the virtual address to the 21 bits inside of the physical address, because your physical address has 33 bits long. So your physical address is 33 bits. So then let's look at an example. Suppose we would like to do the mapping for a 20 bits to a 32 bits virtual address to the 32 bits virtual address to the 28-bit physical address. Again, the lower 12 bits, we do not need to do the translation. And we only need to map the 20 bits left in the virtual address to the 16 bits left in the physical address. So you always, first of all, understand how big is each page. And suppose each page is 4 KB. That actually means there are 12 bits used as the page offset, And we do not need to do translation for those 12 bits. We do not need to do translation for those 12 bits. And then you will just need to cut 12 bits out from your VA, 12 bits out from your PA, and then perform the mapping for the leftover. So then let's look at a detailed example. Suppose this is the given information. So the given information for you is the page size is 4K bytes, 4K bytes. So the page size is 4K bytes. So given that the page size is 4K byte, so we do not need to map the lower 12 bits, inside of the PA and the VA. So we can just, separate, divide the VA and the PA, VA and the PA into 2 pieces. So the lower 12 bits does not need to be translated. And there will be 20 bits left, and it is for sure 20 bits left because you have the virtual address always 32 bits long. So you will have 20 bits left to translate to the physical address. And suppose I gave you this table, which is your page table, and ask you to perform the translation, then can you write down the physical address? So by checking the table, then each 20 bits is actually mapped to a 16-bit. Is actually mapped to a 16-bit because your size of the physical RAM is given. The size of the physical RAM is given, and that actually tells you, for example, the size of our physical RAM is 256 megabyte. And then that actually means you will need 28 bits inside of your physical address. And the lower 12 bits does not need to be translated. So you will have 16 bits left. And if, so then the page table does the translation between each 20 bits number to a 16 bits number. So for a 20 bits number, of course, you have 1, 2, 3, 4, 5 hex characters. You will need to use 5 hex characters to represent each 20 bits number. And you will need to use 4 hex characters to represent each 16 bits number. So suppose 00003 is mapped to 0006, and then how to find a given address, virtual address, the mapped physical address, right? So you could look at the first 20 bits and check this table and figure out what is the starting address of that page, and then you will be able to figure out the physical address of the given virtual address. So another example, suppose we would like to find out the physical address. So this example will be what kind of problem you should expect for your final exam. Okay? So, for example, suppose we have the 32 bits virtual address given as 0003204. So this is a 32 bits long virtual address. And we would like to figure out the physical address according to the page table. So the page table is given, and the page size is also given. So the page size is 4K bytes. So that actually means we need to use 12 bits as the page offset. So 12 bits actually equals 3 hex numbers. So 3 hex number should be used to represent 3 hex characters should be used to represent 12 bits, right? So of course, then the lower 12 bits of the virtual address and the physical address should be exactly the same, So the 204 is actually given. So if you see 204 as the lower three hex character in your virtual address, and you should be able to figure out the lower three hex digits, hex characters in your physical address, because the lower 12 bits should remain the same. So you just copy the 204. And then what is the other part of the physical address? Remember, we need to use the page table. So the higher 20 bits inside of the virtual address should be mapped. The higher 20 bits inside of the virtual address should be mapped to the higher 16, is it 16? Yeah, to the higher 16 bits in the physical address, because your physical address is given, the size of your physical RAM, is given to be 28 bits word physical address. So 256 megabyte is the size of your physical RAM. So you only have 16 bits left for the upper part of your physical address. And according to the page table, the virtual page number 00003 should be mapped to the page number 0006. And why I have to use 4 hex characters here? Because I have 16. So the this number has to be only 4 digits, only 4 hex characters, because it is 16 bits long. And this number has to be 5 hex characters, because it is 20 bits long. So we map the 20 bits according to the page table to number 6. And then if I ask you to write out the physical address, and then it should be 0006 204, because 204 you just need to copy. And the 0006 is given by the page table. So suppose I tell you the size of your physical RAM, give you the mapping table, tell you the virtual address, and according to the virtual address, you should be able to write out the physical address. And this is what is required for your final exam. Okay, so you have to know this example, and it will be for sure on your final exam. All right, so another thing I would like to talk a little bit about page table is called page fault. So we all know that we could have, a smaller, and even you have a big page, you have a big RAM installed. This could happen sometimes. Suppose you do not have the page table entry mapping to the RAM. So some page is mapped to the hard disk, right? Such as the previous example. Suppose you have a few pages in the RAM installed. However, you would like to use some other data which is not mapped to the RAM. So that piece of data is currently on the hard disk. And what it is called a page fault. Right? So the page fault actually should be handled by the operating system. So what will happen? Suppose you have a page fault. The hardware will jump to the operating system. So actually, your hardware helps you to handle this. So the operating system knows, oh, there is a page fault. So I do need to, help the memory access right now. And then the operating system will choose a page, to delete a page from the RAM, because you need to move another piece of data in the hard disk to the RAM. So you might not be using all the data in the RAM right now. So you will delete some data which is not currently used. So evict one page from the RAM and write it. You have to keep it. You cannot just throw it away, right? So you have to put it in the hard disk. Write it in the hard disk. And that page may be on the hard disk originally, or that page may be changed. So if you have that piece of data which is not changed, so you could, just find it in the hard disk. If that piece of data in the if that page of data is actually changed, So that means you have changed it in the RAM, but you don't have it in the hard disk, and then we call it dirty. We call it dirty. If that's the case, then you have to copy it to the hard disk. So before you delete something, before you evict something from the RAM, of course you need to save a copy of that in the hard disk. And now you have a little bit more space open released for your new data. And then what you could do, the operating system could move the page you want to use from the hard disk into the RAM, and then update the page table. So what actually happened here is what we discussed before. So like if you would like to use certain data, and then that piece of data was originally not mapped in the RAM. It's not mapped in the RAM. So it's actually, pointing to the hard disk according to the translation table. So the operating system will help you to deal with this. So first of all, I do not have it in the RAM. And what I can do is, I can figure out there's a piece of location which is, able for me to use. If you have everything in your RAM, like the RAM is full. If the RAM is full, then you have to determine, well, maybe I need to copy this to the hard disk, copy another piece of data to the hard disk, and then we call it evict that piece of data from the RAM, and then you will have some space open right now, and then I can move the data I want from the hard disk into this location. I can move the data I want right now from the hard disk into this location. And then the table should be updated. And then you have the mapping, pointing to the RAM, and you will be able to load from RAM. So this is the example we have talked before. So, but this is called page forward. This is called page forward because it does cost you a lot of time. And how much time it should cost? For example, so this page listed, how long it will take. So the page table says the data is on the hard disk. It's actually just a one machine cycle. However, your CPU need to generate a page table page forward exception, because your CPU see that and your CPU need to handle that first to give a signal, right, to the operating system. And this could cost you 100 machine cycle, which is okay, 100 machine cycle. But later on, suppose the operating system need to move the data to the hard disk and then move the data from the hard disk to the RAM, and each step could cost 2, 3, 4, 5, 6, 7, 8 can cost millions of machine cycles. So overall, this whole process could be 80 million machine cycles. So that's a super huge number, right? So comparing running a certain program. So this way okay, how slow it could be if you want to read something from the hard disk. So the page table are the slowest possible thing that could happen to a computer, except human interaction. So don't complain, because we are even slower than this. So except the human interaction, then the slowest thing you could see inside of the computer will be the page forward. So caused by reading something for hard disk and reorganize your page table. So this is how we actually use the whole memory. So we will stop here. And with the virtual memory technique, I hope you can have a better understanding of how the memory hierarchy for a high performance computer look like. So we have introduced the virtual memory. Then you know how to deal with how to actually use the hard disk, and we have also introduced the cache design, so you know how to make the memory access to be more efficient. And so this actually includes the most important concepts of the high performance memory design. All right, so I will stop here, and in the next video, for next week's video, I will introduce different technique is pretty much introducing the concepts for other parallel processing concepts, high performance calculation, high performance computing. And then I will also have a video. To briefly go through all the required topics for your final exam. So I will generate a review list, and I'll go through the review list briefly to help you get prepared for the final exam. All right, I'll stop here.